Hi, today we're going to talk about x and y intercepts. Right, there would be an x-intercept, and here would be another x-intercept. An x-intercept would be the place where your function or your line crosses the x-axis. That's why they call it an x-intercept. This would be the place up here at the top, would be the place where your function crosses the y-axis, and that's called a y-intercept. You're going to be asked to give me x and y intercepts. You should be able to read them off a graph, and you should be able to calculate them algebraically. First, I'm going to show you how to read them off the graph, and then we're going to get them algebraically. So first up, I'll write down the x-intercepts. There's a couple of different ways to write this. In order to tell me that you know what the x-intercepts are, ooh, crazy looking T, you could say the x-intercepts are x equal, and if I'll notice on the graph, it's a positive and a negative 2. Those would be the x-intercepts. The y-intercepts, well, there's only one, and it's y equal to 4. Another way to write this is you can write them as coordinate points. So if someone asked you to label the intercepts, you could say they were at 2, 0, at negative 2, 0, and we also have one at 0, 4. And this would be labeling them as the coordinate points. We're going to calculate the x and the y-intercepts algebraically. The x-intercepts, as we saw with the coordinate point, are the place where y is equal to 0. So we'll substitute a 0 in for y, and we will get 4 minus x squared. We're going to need to solve this for x. So I'm going to add x squared to both sides, and I'll get x squared equals 4. Then I'll take the square root of both sides. And when I take the square root of both sides, I do need to remember my plus minus case. Oops, I wrote that a little close there, but you get the message. And so x is going to be equal to, so I'll rewrite that, plus minus square root of 4, and then we could say that x equals plus minus 2. And this particular x-intercept, these two, occur when x is 2 and y is 0, and also when x is negative 2 and y is 0. And we saw that pictorially on our graph as it crossed the x-axis. Y-intercept. In order to find the y-intercept, that is the place where x is 0, so we'll plug in a 0 for x. So this would equal 4 minus 0 squared, which equals 4. And as writing this as a coordinate point, I would then write it as x is 0, y is 4. You can write this either of these two ways. You can either write them as coordinate points, or you can write them as x equals and y equals. Here's a cubic function for us to look at. In this cubic function, we will see that it crosses the x-axis and the y-axis in one spot each. So there's where it crosses the y-axis. Here's where it crosses the x-axis. I would write this as, whoops, there's a star there. Nice. Let's go get my pen. X-intercept occurs at, looks like x equal negative 1. Now you'll notice as I'm doing this, I'm saying it looks like and it's about. The reason for this is whenever I find the x and y intercepts graphically, really it's just an estimate. It could be 1.1, 1.2, I don't really know. It could be 0.95. I get an estimate or a good guess as to about what the x and the y intercepts are based on my scaling and how accurate I am on my graph. Now when I find the x and y intercepts algebraically, then I get a very nice, accurate, exact answer for my x and y intercepts. I'm just going to do that on this grid right here, and I'm going to find the x-intercepts and the y-intercepts algebraically. Meaning that whenever I'm looking for the x-intercept, that's the place where y is 0. So I'll plug in a 0 for y, and I'll get 0 equals x cubed plus 1. I'm going to subtract 1 from both sides, so I'll get negative 1 equals x cubed. I will then take the cubed root of both sides, represented as such, and I'm not sure I'm going to be able to squeak this little 3 in there, but there he is. And then I get that x equals the cube root of negative 1, which I can then say x equals negative 1. I'm looking for the y-intercept. I'll substitute in 0 for x. This is my favorite one to do because I don't have to solve for anything. I just get to plug it in and compute, and then I get y equals 1. Accordingly, I can write these intercepts as negative 1, comma 0, and I can write it as 0, 1. There's my x-intercept and my y-intercept. All right, we're going to discuss different symmetry on the graph. First off, we're going to look at y-axis symmetry, then we're going to look at x-axis symmetry, and we're going to look at origin symmetry. Y-axis symmetry occurs when a graph is the same on the left side as it is on the right side, or in other words, on either side of the y-axis. You have the same exact shape identically. It's as if I took a wire on one side and flipped it over the y-axis, and his picture is sitting over there on the right. So if I took it from the left, flipped it over on the right, or the right and flipped it over on the left, either way it'd be the same thing. They're going to ask you to prove this algebraically, and how you will do this is you will show that f of x, f of negative x equals f of x. Okay, I can demonstrate this algebraically. First off, I have that f of x equals x squared. So let's see what f of negative x would be equal to. In doing this, I substitute a negative x in place of x, and I need the entire x squared, and my x happens to be negative x in this case, and negative x times negative x is positive x, which in turn then equals f of x, thus proving that y equals x squared has y-axis symmetry, and I've proven that algebraically. Now it's nice to be able to look at the pictures of these so that I can tell whether or not they have axis symmetry. That's usually the easiest way, but sometimes you don't have a picture, or sometimes they ask you to do it algebraically. Symmetry, you will see it's as if I took a wire and I flip-flop that wire across towards the diagonal of, it's as if I took this piece right here and flipped it down and then back across. So it's like a flip-flop, or you can say it's symmetrical in diagonal quadrants. In order to prove algebraically that a function is or has origin symmetry, you will need to show that you have the following. So my function is 2x cubed, and I'm going to then try to determine what f of negative x looks like. So that's going to be 2 times negative x quantity cubed, and that will equal 2 times negative x times negative x times negative x is going to be negative x times negative x times negative x, which will then get me negative 2x cubed, which then equals negative f of x. And I've shown algebraically that this function has origin symmetry. In looking at x-axis symmetry, we need to show that if we replace y with a negative y, we will result in an equivalent relation. And we will, because the absolute value of negative y is going to be the same as x equal to the absolute value of y, thus getting me the equivalency. So x-axis symmetry is basically just taking and pretending like we have a wire on this top end right here and flipping it about the x-axis and seeing if we have exactly the same picture that I have on the top side or the bottom side to the top side, whichever one would be the case. Whoops. And that's it for symmetry and intercepts.